Hello, welcome back. In this segment, I will prove some elementary properties of integer division. Let us assume A, B, and C be integers. They can be positive, negative, zero. We don't make any assumption. They are just integers. The first property is that if A divides B and B divides C, then A divides C. Let's prove that property, right? A divides B means B is equal to Q times A. What about B divides C? That means C is equal to some R times B, right? That's the meaning of the definition of divides. Okay, now I can substitute B into this one, which means C is equal to, this implies C is equal to R times Q times A. And because multiplication is associative, I can rewrite it like this. So C is equal to R times Q times A. Okay, this implies that A divides C because that's the definition of divides. So we proved the first property. All right, let's start with the second property. A divides B and A divides C implies A divides any linear combination of B and C. Okay, X and Y are integers here, although I have not explicitly spelled out. How do we prove this property now? Since A divides B, we can write B is equal to some Q times A. That's the definition of A divides B. Okay, and what about the next one? A divides C, that means C is equal to some R times A. In order to prove Bx plus Cy divides A, I need to first construct the expression Bx plus Cy. X and Y are some integers, okay? So what is Bx plus Xy? Bx plus Xy, Cy rather, is just QAX plus RAY, right? And now I can take A common, which means I have AS common, and I get some QX plus RY. Okay, just taking A common. This means that this implies immediately A divides Bx plus Cy, because you can see that Bx plus Cy is written as a combination of A times something. Okay, that's the definition of divides. This is the quotient. This is the whole thing is a quotient, and we got this done. Okay, so this proof is done as well now. Let's move on to the third proof now. Third property says when A divides B and B divides A and B must be equal to each other, but they can also be opposite of each other in terms of sign. Okay, let's say A divides B, which means B can be written as some Q times A. Okay, and also B divides A, the next one. That means A can be written as some R times B. Okay, both Q and R are integers, of course. Now I can use B in the next one. That means I can rewrite the second one as A equal to R times Q times A, right? Which means I can just move around my A. I give a 0 here, and I take a common, and then I take RQ minus 1. Okay. Now I have a product of two things being 0. That means one of the thing must be 0. Okay, so there are two possibilities. Either A can be 0 or the next factor can be 0. Let's assume A is 0 for a moment. If A is 0, it's simple now. If A is 0, what can you say about B? You can just go ahead and substitute here, right? If A is 0, B is also 0. So the property is already proved in the case when A is equal to 0. Okay, so let us assume now A is not equal to 0. When A is not equal to 0, what you're having is that RQ will become 1, right? Otherwise, you will not have 0 there. Well, when RQ is 1, when what can you say? R and Q are both integers. So the only case when R and Q, when you multiply, becomes 1 is R is equal to plus or minus of Q, plus or minus of 1. R and Q are both equal to plus or minus of 1. Okay, they're integers, right? Therefore, this is the only possibility. Okay, that means now you can go and substitute it here. wherever you like. B is equal to Q times A, but we know Q is plus or minus 1. That means B is equal to plus or minus A. Okay, which is exactly what we need to prove. The same as saying A is equal to plus or minus B. If you prefer this one better, R is equal to plus or minus 1, therefore A is equal to plus or minus B. All right, so we proved third property as well. So remember, A divides B, B divides A doesn't mean A has to be equal to B. It can also be plus or minus B. All right, let's move on to the final property. So what is the meaning of A divides B? Well, it means B is equal to Q times A. Okay. They also tell us one more thing. They said B is not equal to 0. So since B is not equal to 0, what can you say about Q? Q cannot be 0 either, right? If Q is 0, B will become 0, the contradiction will happen. So Q is not equal to 0. Okay. What can you say about absolute value of B? Absolute value of B is absolute value of B means if you send in a negative number, you will get the positive equivalent of it. So absolute values are always non-negative values, okay, which is nothing but absolute value of QA, which is nothing but absolute values are computed before multiplication is same as computed after multiplication. So we can write it like this. Okay, so what can you now say about this equation? Absolute value of B is absolute value of Q times absolute value of A. So you're able to write one number as a multiple of two other numbers. That means the left-hand side number must be greater than each of the right-hand side numbers, right? We are dealing only with integers, there are no fractions. Therefore, we can immediately say that B must be greater than or equal to A. All right. This is because absolute value of Q, this is because absolute value of Q is greater than or equal to 1. The reason why I say greater than or equal to 1 is that Q is non-zero. Okay. If Q is non-zero, absolute value of Q must be greater than or equal to 1 because we are talking about integers. So we proved all the 4 properties. These are fundamental properties. We will leverage them later in our cryptography course. Wonderful. Thank you very much for your attention.